This is a piecewise linear algorithm.
Hello, YouTube. How are you
hello.
doing? Hey, Ben, how are you?
Flustered, but well, it's always good to see you, Bill. And Mike, always great to see you and have you on as a guest. Thanks for joining us today, because you've got some pretty cool stuff to show us. Hey.
How you doing?
And,
yeah. So what we did this week is Mike and I played with Spice, and Mike had not used LT Spice, which to me is the lowest common denominator. Ben, would you agree that that's just not a bad starting point if you want to learn Spice, or do you have a better one?
I'd say it's an excellent starting point, and the one most people start with, because it's free.
Okay.
And so I'm just kind of looking around.
Yeah, like Bill sent me
browser tabs. LT Spice. It's funny you said lowest common denominator, and my immediate reaction was, "Ooh, some people probably just got offended."
Why? Then they can make their own and make it free and easy to use.
People love it. People love it because it's free, right? And it came from Linear Tech, and the reason I think it took off was they pre-packaged all their libraries of, switching regulator controllers and linear regulators. And so people were using it to design voltage regulator modules and power supplies.
Mm-hmm.
And it was just free. And they had the library built in with all the models. So you could wire something up and get it working in simulation. To me, the biggest problem with Spice was always the setup. It's such a pain in the ass. And LT, if you were using their components and following along with their application notes, remember they used to put out those app notes that were in that nice thick paper with the red print?
Yeah.
And like you could follow on with those, and then LT would already have all the models built in. So you didn't have to worry about hooking things up or hunting for a model.
Right.
Most people use Spice but don't write their own models. Very few people write their own models.
Well, you want the manufacturer's model if you can get it, most often too. Which most manufacturers, if you look at data sheets and look at, websites and whatnot, a lot of times there is a little icon that says Spice model. And
I've seen that, and I've never paid attention to it until now.
And one of the things that worked out so well this week, so what we did this week was, I wanted to make this signal right here, boink, and see that's that little squiggle in the green on the left is what's called a tri-level sync pulse, and it actually goes negative 150 millivolts, positive 150 millivolts, and that's it. And then it's blank for another horizontal line. And so I was like, well, how can I pick that off and turn it into a pulse? And on top of that, without shortening it to ground when it goes below ground. And on top of that, how can I do this with a 5-volt supply only? All right. Because this is going into somebody's Arduino-ish type thing. And so instead of plus or minus 12, like you might do for an op-amp circuit, I was like, hey, let's do it for plus 5. So I challenged Mike over the week. I showed him a circuit, and then I showed him Spice. And boy, that was like an oscilloscope for you, wasn't it, Mike? You were able to just pick that right up.
To be honest, I had your help. To be honest, it was kind of like for me, that tool was kind of janky to get going with, but you were there to help me get it going.
Right. And that's why we're here today it's a horrible editor, right? And what I didn't know was in a Mac, there is no editor. You have to know the hotkeys. Did you know this, Ben? That in the LT Spice on a Mac?
It's different. So even Bill was kind of like flummoxed a little bit there. And he's like, how?
I had to share a screen. Yeah. And then when I shared the screen, I'm like, no, your menu's missing, dude. And so he has to do F9 for undo and F5 for cut and whatnot.
That's odd because Mac does do the menus differently, but it sounds to me like they did something wrong for the port, because the menus, Mac always has that top menu bar, right?
Yeah.
It's always there. So whatever program is in focus ought to automatically update the top bar.
Yeah. So the main
And,
difference in my mind in the UI is there are some buttons in the little button bar where, like, if you want to click to just make a resistor or something like that,
Okay.
And
those
they
buttons
work
exist.
really good.
There's a few buttons there, like there's the little running man and a hammer, but they chose not to have all the other ones.
So this was
we were
LT on Mac? I didn't know they had a Mac port.
Yeah.
Well,
So,
my question is, why would you
Okay,
use a Mac port? But then I'm not a Mac person, right? I'm like,
just trying to keep you on your toes, man.
yeah. Well, now, do you like the Mac really for doing everyday work on, or do you keep a Mac to do testing with alternative operating systems?
So no, I use the Mac all the time, and I'm inherently identify as a software developer, and I but to be honest, getting into this hardware stuff, I need a PC to run things like Proteus and other tools. So I have another PC near me. Yeah.
I think a lot of software people have moved over to Mac. Most of the software developers I've worked with in the last 5 years are, 80+% of them are.
Yeah.
They prefer Mac because the tools in the GNU tool chain, and also even Microsoft Visual Studio, runs on Mac, and you can make cross-platform, and all the build tools and Qt, the libraries you use, all that stuff. Mac's just kind of it's
good.
all gone that way.
Yeah.
So
I'm not going to try to convince you to use it, but I can use any of them. Yeah.
No, I was just curious if you were doing Mac specific, or you liked the paradigm of working with a Mac. It's easier to use for software development.
Oh, I think I could use almost anything for software development, really. Yeah. But yeah, those are like religious arguments, right? You get into those kind of,
Well, I wasn't trying to start one. I was actually, in this case, I was going, how useful is it for you?
Yeah.
I am starting to feel tense though in this discussion.
I like the Mac, but I'm not that religious about it.
Yeah.
I think the reason why it works is because it's actually really BSD under the hood, and so most software developers love Linux and BSD distributions.
You can get a Unix prompt, basically.
And it's like, if you're very comfortable in those environments and you know where to go, it's all the same. But for me as a hardware, I'm mainly a hardware person, and I've been on Windows. My first computer that I had daily access to was actually a PCAT. I've said this on the show before, a 286 clone running DOS. And that's just how I grew up. And I've played with Linux and here and there throughout the years, but I never decided to fully adopt it, because all the specialty I have is in CAD tools that for the longest time only ran on Windows. So I'm like,
that's what happened to me with Proteus, and even playing around with Altium. It's like, you got to have a PC for this.
Yeah.
Or you can try to run stuff in parallels, but that is slow. That's dog slow.
It's painful. Yeah. VMs are kind of, to me, they're very useful for other things.
Mm-hmm.
I actually this week started playing with source code for open source synthesizer. There's this very well-known designer. I think she's a French Canadian engineer who designed all these open source audio synthesizer modules in the Eurorack format.
Okay, yeah.
Called, gosh, I've got a website open here. I forget her name exactly. It's a French name that's hard to describe, but her company is Mutable Instruments, and all her modules are open source, so people can copy or tweak them if they want. And she put her whole development environment on GitHub, and
as a VM kind of,
well, that's the thing. Like, you just you clone it, and then you run Vagrant, and it automatically builds a VM in VirtualBox, all done through scripting. But you can stay in your own editor and your own whatever environment you like. So it's like this isolated bubble you're talking to. It's really cool.
Yeah.
Anyway,
so Bill sucked me into this whole LT Spice thing, and I found it fascinating. It was basically, Bill had, like, he described this little problem of basically, like, can you detect this little blip? And can you turn it into a TTL level pulse?
You started showing us that waveform there, that 3-level sync pulse.
Yeah, and I've already pulled it down. Here was the circuit I ended up doing, and there was just enough nodes in the circuit that I was like, before I shoot this PC board, because I'm known for that. I don't like the breadboards very much because I do analog, and the breadboards don't lend themselves to analog. So I did this little circuit, and then I got on the phone with Mike saying, hey, here's the circuit I'm messing with, and I'm going to spice it. And we got into LT Spice. Now, one of the things...
Why did you do it in LT Spice and not directly in Altium?
Because Altium is so freaking hard to make sure you've got all the models, and I didn't even know where to start. It's been more than a year.
So Ben, what happened though? What was cool?
I will tell you though, they actually introduced a wizard in version 21 or 22 that's brand new that you don't know about. I'm going to make a video of it on my channel probably next week because I just went through it, but I can show it if you want later. But this is the whole thing. It goes back to why LT Spice is a great starting point and why people love it, because it's free and it's just what everyone uses.
It's ubiquitous
by default.
Yeah, right?
It's the default.
Yeah. So Bill was he started giving me copies of his LT Spice models and or files, whatever you call it, right
through Discord. Our Discord channel, which you can get to at Coriolis-effect.com.
and the next thing you know, I'm like running Bill's stuff and tweaking it on my end. It's like, that's cool.
It's perfect.
Right.
But these models, they're standard. That's the nice thing about Spice. Most Spice simulators all use the same. They're all based on the same Berkeley Spice under the hood anyway.
Yeah.
Almost all of them.
Right. So you might as well use a free one. That's kind of... Now, with that said, why would you use it in Altium? Well, the answer would be, well, if I've drawn a complicated circuit in Altium, why would I want to go and redraw it? And that's what I've done here is I've redrawn that schematic I was just showing you a bit ago. I've redrawn it in LT Spice. And yes, it was arcane. And yes, it's hard to move stuff around. But it's actually, it's pretty straightforward too. You can, let me get my mouse in the right screen here.
But also, Bill, you were able to give it to me.
Yeah,
like, I don't have Altium.
anyone can do this. There's another trick. Mike, I can generate something in Altium and send it to you, and you can run it in LT.
Nice.
Because I can just send you the Spice netlist, which doesn't mean it means you don't require the actual binary schematics or nothing.
Yeah.
So let's talk about what is Spice before, because I want to show, because I had to make this symbol, and it was actually very straightforward. And if you learn nothing else today about Spice or LT Spice, I started to use a quad comparator, the LM339, which is not part of the Spice library, but I grabbed it off the TI website. I open it in Spice, and then I click on it, and you can't see the screen that came up, but it says make symbol. And so I
like that.
I made symbol.
Really nice.
And then I go over to my schematic. Whoops, let me get on the right thing. I go to my schematic, and when I go to place a component, now it's built in automatically. There it is. I didn't have to do any work, and it's a manufacturer accurate symbol, so I'm good with it.
Well, so I guess it's good enough for simulation. Let's put it
for what I do. Oh yeah. I actually.
That's just a symbol for the 339. You couldn't map that to a footprint and use it for PCB layout. So that's a pretty key difference.
Oh, you're talking. Yeah, there you would want like an IBIS model or something like that. Then
no, you need actual pins. This shows. So here's the thing. The LM339 is a quad comparator. There's 4 of them in one package.
Right.
So if you download lm339.txt from TI or whatever,
which is right here, it's only got one set of pins. That's absolutely correct. Yeah,
they've got one part, but the actual manufactured package has that 4 times assigned to different pins. So this model is only good if you generate a symbol only from this. It's only good for this simulation, right? Like you can't. I don't think LT Spice was ever geared towards anything other than simulation. Correct me if I'm wrong, but you can't export a netlist from making a board from it, which some of the Spice simulation tools out there, like Microcap, you can actually generate netlists for various PCB layout tools. If you want to do all your schematic and engineering in microcap you can.
Right. Right.
But,
So no, you can export. So yes, it's kind of a dinky little. Let me see if I can actually run it here. It looks like a dinky little program, and yet it's so powerful. Let me.
everyone uses it like it's people trust it, and there's a reason why people use it, right?
Yeah. Yep.
It's
So
one of the tried and true ones.
So I'm going to come up. I've already made my circuit. I'm going to come up and I'm going to click the little running man.
Okay.
And this right off the bat, I get a blank screen. And if you don't know what to do, you hover over your schematic and you left click, and there is the stimulus. Now, this stimulus is very cool. I want to show you how Mike did this. This is this is NTSC.
That's not a normal stimulus. Like you could try to generate that using Spice syntax, PWL. You'll have a very hard time.
Oh yeah.
Right.
That looks like something you actually captured and then.
So that's what we were doing.
That's what we did this week. Was we played with capturing it right off our scopes. Now my scope didn't do it as well as Mike's did, but Mike wrote a program that took the capture and converted it to piecewise linear, which is the name of the stimulus. So I know we're jumping around here all over the place here, but let me go. But
yeah, initially I was just making remember you had me like I was using my little signal generator just to make the little blip, right?
Right.
And you're like, hey Mike, can you like make a little circuit that would like find that blip? And my reaction was to just like amplify it and then throw it into a 555 to like pulse extend it. And
we simulated and it worked.
Yeah, that worked. Yeah. So
we found 3 answers, and that was the beauty of Spice this week. Was we found 3 different answers to how to do this tri-level sync pulse. And as it turns out, my circuit worked with an NTS sync, but I don't trust it because I designed the circuit. I know it wasn't made to work with a true NTSC, the green here that you see. But it actually did the job of finding that negative going pulse from a baseline. And there's actually something interesting in the circuit. Ben, if you look here, I've got a differentiated input here, or AC coupled, as we say, but I have a filtered input. And so that's like the past.
It's a delay.
It's a delay and it's filtered. So it's an auto baseline. No matter what the baseline is, it'll track to it slowly. And then I find any quick pulses that come off of it relative to that slow tracking bias.
Right. So pin 1 and 2 on the comparator, are those, which one's inverting and which is non-inverting?
The not inverting is 1. And that's the only bad thing here is I didn't draw the symbol so that it's actually viewable. But it's the opposite of the.
Go back to your Altium schematic so we can look at the actual. Look at it that way again.
Sure.
If you want to describe the circuit there.
Yeah, that makes sense.
And to be honest, this is cool because I would breadboard things like this, but you can't easily probe around like you can in Spice. You can, right, on a breadboard, but it's like so much faster in Spice to just click on all the things.
When you get this. All right, so here's the circuit. So basically, it's like, well, how do I find a negative going pulse when I don't know what the rest of the circuit the rest of the waveform looks like? And so this is a technique I learned. I took apart a depth finder from an ultrasonic depth finder back in the 80s. Yes, I was working on the backup alarm for cars when I took apart a depth finder, so I was learning tricks. And what the depth finder did was when it first does a pulse, it wants a high reference to compare to, but then as time goes on, the signal gets weaker and weaker. So this would track the baseline after each ultrasonic pulse.
Decay, yeah.
And so it if you just did an absolute value, it would swamp it in the beginning and be too small on the end. So you need something that adapts. So this is an adaptive baseline for a comparative.
If you put a stock chart into this as a waveform,
that's what I was suggesting. To build was a stock chart. Yeah.
What you have is a moving average filter. That's your RC.
That's it.
Yeah.
Yep.
And the time constant is set by RC, and your comparator is giving buy and sell signals.
Yep. Yep.
Oh, okay.
When the
And then-
Okay,
when
when
the
it's low.
stock price quickly makes a change, positive or negative, around the moving average, and
Right.
crosses the line. So this is why electrical engineers often make very good traders. I'm not. I never
Yeah,
had
you
the
could
guts
become a
to
quant, right?
go that way. But I know of a lot of traders who started out actually studying electrical engineering, and it's like they're just applying the same signal processing signals into stocks and then using that to make buy or sell decisions.
Right. So there's one other interesting thing in here, and it's like, well, now I also need a pulse stretcher because that initial waveform was short.
Yep.
How do I make it into a long pulse? Well, the LM339 is an open collector comparator. And so I set the polarity. I could have made it high when true or low when true. And I made it that when I detect the signal, this grounds this capacitor. And it does it very quickly because there's no R. It's just the output of the transistor.
Yeah, those are open collector outputs, right? They're 339, is that right? Yeah.
Right, that's correct.
It shorts it out.
And then RC charges it. So I can pick this RC time constant here to turn it into about a 4 microsecond pulse. So that's the second part of this, the magic juju of an LM339 circuit like this is you use the open collector for everything it's worth. You can actually do audio detection with it, all kinds of things. But I slam it to ground, low impedance, and let it drift high under R, whatever R that is, R3. And if I show the circuit again, now that I've explained that,
your simulation, I could see that in the waveforms. So it generates a fixed with negative pulse on detection.
And so there it did it. And I've actually plotted in blue. It's hard to see, but in blue, that's the actual RC value too.
Can you easily edit the waveforms, like make the colors brighter or thicker, or can you do that?
No, you can.
No, it's LT Spice.
You can make the lines thicker, though. I noticed that. You can click on.
Oh, can you? Okay, so I'm learning something here. There we go.
On the Mac, you can. Yeah, There's a place where you can click. If you're editing the chart, you can put the hammer on the chart, and then you can make the lines thicker and whatnot.
You've got to be able to click on the line and adjust it or something, right?
Yeah, I can highlight that, which makes it harder to read.
For me, on the Mac, the little hammer, the whole chart is a separate window, and you can edit the configuration of the chart.
Yeah, if you go to plot settings, there's probably something in the menu for plot settings. If you select the plot window.
Yeah, select the plot window first, or maybe you already are. And then hit the hammer button. Or does it? Yeah, go in the plot settings in there. Compression. Waveforms, yeah. And then in there you can set the trace width is 3. Make it bigger and
there we go. All right, I learned something. Excellent. I learned it from a Mac guy.
Yeah, those lines start off pretty thin. My eyes are too old to see that.
But so what's cool here, and this is what Mike was talking about, you can go in and I say, well, I want to look at that bias circuit that they were creating, and there it is. So we see that it's now there in blue. We see that when the yellow waveform crossed the blue, that's when the red tripped. And that's the beauty of it. Is before I build the circuit, I can go probing around all over the place on this thing and make sure it works the way I thought it did. And change component values. I actually picked my capacitive value. So let me show that real quick. So I go in, and I'm going to change this to...
What's that called? Is it called cut and try? There's some term you use for that, where you just try different things to get
the herd method. Yeah,
the herd method. Okay.
This is what Spice really did for electronics designers, though, was it made the design process way more experimental and less scientific.
Synthetic
Yeah,
so,
I mean, you can... I still think the most efficient way to design is honestly to calculate what time constants you want
Right.
It's circuit like this, like you actually do the math, because it's not difficult
It's really
math.
hard. Yeah.
You're not doing calculus. It's just simple formulas. So
Yeah.
work it out and say, well, this should be about right. Then you simulate it to verify that you haven't made a silly mistake. Then you build it and measure it and confirm. But usually simulations can not usually, but often the simulation will be very different than what you actually measure. Especially with oscillators.
Yeah.
It's very easy. It's super easy to make an oscillator in Spice, and you'll see it'll start up and it'll oscillate. Then you'll breadboard it or put it on a printed circuit board and it won't start.
Right.
Because just tipping it, getting it to tip into that perfectly underdamped part of the S plane where it's right on the boundary between stability and instability.
One thing I found was I did one of these circuits in Spice, and then I actually went and built the real thing, right, and hooked it up, and I found that it was behaving differently, and I found that what I hadn't modeled was the input impedance or the effect of the input impedance on the source,
right?
And because my little blip that I was generating with my signal generator was being harmed, it's kind of being pulled down. And in Spice, it was looking perfectly square, and so I went into there and changed it and gave it some parasitic whatever.
That's right.
ESR,
so your general out of the box.
Yeah.
This is the other thing with Spice. It's difficult, right? All the out of the box sources and Spice circuit functions. There's libraries of special functions like integrators, differentiators, multipliers, like basic math functions that you want to put, and all of them out of the box are ideal. So you have to you have to do stuff with them to make them more like the real world, and that's where the setup gets challenging.
Right. So here I've changed the stimulus by selecting a different file, so it's no longer an NTSC line. Here's that little squiggle, and this is called a tri-level sync pulse. This is used in Genlock for. Oh, let me show you my cool Genlock generator I just got.
Tri-level sync pulse sounds like a fancy name for what it is.
It is.
I prefer the word
it's not what I thought it'd be when I looked it up. But I was playing with a sync generator that generates both standard definition and high definition Genlock signals. Oh, man, so that's cool. So I was doing a half mixture of actually having a real signal in Spice and comparing the two while I was working. And so Mike didn't have the original signal originally.
I have the same thing you do.
Then he built one. Yeah.
There's this this NTSC generator that Bill has. I ended up buying the same one, off eBay.
Right.
And that's when Bill said, "Hey, Mike, can you capture that and send it back to him?"
So
that's mind blowing. Yeah.
What we've done this week is we've got the signal. We're recording it from a generator, and then we can load it into our arbitrary function generators and play it back. So we could post that. If Mike could post that to the Discord channel, if you want to turn your arbitrary function generator or your Spice into an NTSC stimulus, we captured it and made a file out of it.
I was surprised in that I thought it would bring LT Spice to a crawl, because I thought, oh man, you now have this PWL input that's got a lot of points in it, and I thought it would just kill LT Spice, but it actually was fine. I think you were just using it before, Bill, right? It's fine,
Yeah. So Ben, what Spice do you like?
I like microcap. I used only because I got to know it pretty well when I was doing my engineering degree years ago. It at that time they had a free student version. It was to buy the full thing was like $4,000 or something. So I never got that. But then just recently, maybe 2 or 3 years ago, the developer of that software decided to retire and make it free.
Oh.
So it's got a very late 90s user interface, which tons of tiny little icons on toolbars, which I hate, but it's very, very powerful. I'd say it's it's got almost equivalent capability to OrCAD's PSpice, which is kind of the industry flagship, which PSpice is $10,000 or thereabouts. That's the sort of typical price you pay for that. But you get things like smoke testing and a lot of really good extreme values.
Are most of these just GUIs on top of Spice, or do they
No,
improve Spice
PSpice is
under the hood. Many of them are actually that they all came originally from Berkeley Spice, which is open source, but with a BSD license, which meant companies could add to it and make it commercial. The Berkeley Spice had to be entirely driven with text files and commands. And so all of these companies that built the popular Spice tools we know today started out by building graphical front ends for them that made it easy to interact with a schematic and waveforms.
Yeah.
So the reason we used PSpice at one place, though, was they had a better coax model. They didn't do a lump sum coax model, which just models it as a coil and a capacitor. They did coil cap, coil cap, coil cap, coil cap.
Yeah, and distributed element. A proper linear model for transmission lines, which all of them have that now, but they didn't back in the day necessarily.
Now, so back in the day, I called PSpice. I said, "You got your model of coax wrong." And he's like, "What? Really?" I said, "Yeah, you actually did." And so he looked at it. They had gotten so involved with skin effect and all the stuff that goes into it, they didn't do the IR drop of the copper. And that was it. Is they didn't. I had a 500-foot spool of coax or something. And I'm getting like 22 ohms on here, and you forgot to model that part. And he looked. He said, "Son of a." So they forgot the simple part, the IR part of modeling the coax. Now this is 1990 when that happened.
There's so many options though. You know, like LT is a good one. There's so many free options. You can use most of the even commercial Spice tools that are built into ECAD are now based on NG, which was the NG Spice is the descendant of Spice 3 from Berkeley that includes mixed signal capabilities. So it has a whole set of extensions that let you do mixed digital and analog, and it's still maintained as open source, and there's a few different front ends on that.
When it goes into digital, is it doing like just discrete event simulation type stuff where it doesn't care about the actual physical voltage levels anymore?
It does actually mix both. The simulation engine that used to be in Altium Designer was called X-Spice from Georgia Tech, and it was doing the same thing. And it had a C-like programming language for defining the logic at the core, but around that it would actually model different voltages and things. It wasn't just ones and zeros. It would actually interact. So you could have a 74HC chip, and it could have all the characteristics of you could incorporate the characteristics of the lead frame and the voltage levels, and it would pay attention to what power supply voltage you fed the chip. So if you're driving it from 12 volts, it could have a 12-volt output, for example. If it were a 4000 series, which you could do.
Right.
These you couldn't. But there's a lot that have descended from that, which I really like, that are still open source, like Coax Studio, which we've talked about before. But Coax is good because it's got a lot of additional stuff added to it for RF and microwave that doesn't exist in Spice. And it's a whole different engine, but it's completely open source. And they're trying to, so you can combine Spice model-based simulation with some RF if you need to, for example. And it's not too hard to set up. They've got a pretty good library in it, and the graphing. The schematic editor in it's still kind of a little janky, like most open source. You hear my opinion coming out there. There's a residue from being employed by EDA companies, but there's some truth to it. If you have a team of 30 paid software engineers working on a schematic tool, it's going to wind up looking pretty good and being easy to use, generally speaking. If you have a bunch of volunteers who contribute a little bit here, a little bit there as they have spare time, there's only so much you can do. So
yeah, actually, it turns out it was probably HSpice I was talking about. But check this out, Ben. You can get PSpice for free. I just happened to be on the website looking at, because I was looking at multi-format sync separators, which is how I ended up solving this problem, by the way. But down here, it says PSpice for TI request, and I got an automated. I filled that out with my email address, and it was automated. It didn't even, a person didn't have to look at it and see if I should get PSpice or not. So actually, I've loaded PSpice this week too.
That's really good. That kind of reminds me. It's like with the FPGA vendors. You know, they didn't have their own simulations for HDL. So they would team up with an EDA company and offer a free version that was restricted and only had libraries allowed for their silicon. So I ended up with 3 versions of Model Sim on my computer because I had the Xilinx Starter Edition, the Altera Starter Edition, and the Lattice Starter Edition. And depending on what part I was targeting when I ran a VHDL simulation, I'd have to specify which path to Model Sim it had to use to launch the executable, or it wouldn't work. It would throw up saying, "Oh, you don't have a license for these other libraries." So but that looks good. I'll check that out. There's I'm sure it's missing some capabilities. There's no way they'd give that whole thing away for free. But
I'm sure. Yeah.
Yeah. If I'm designing analog stuff in Altium, I will try to simulate in Altium if I want to simulate, just because I don't like redrawing things and I hate other schematic tools.
Right.
Eagle's another one. They put ngSpice in Eagle and Autodesk Fusion 360. So that's another one. If you want something that's integrated with the schematic PCB and Spice, Eagle actually does it really well. So it's all in all of them. It's ngSpice underneath. So it's all the same speed. It's all like same performance, same types of simulation ought to be available. Sometimes, like in Autodesk, they haven't finished the Spice user interface in Fusion like it is in Eagle. So there's limits to what you can do. But yeah, like this schematic here, I'll do that. But the big problem with doing it in EDA tools is you've got to have models for everything. So even your connectors. So what I used to do was make my connector libraries, and I'd add a Spice source, a parameterized Spice source model to the connector. So J1 there is an input. I'd give that the Spice source.
The input stimulus.
Instead of sometimes if I'm just trying to do it quickly, I'll put what's called a compile mask over that. So Bill, what you can do is you go to so select J1. Say you want to leave that out of the simulation because it'll stop and it won't simulate if you have a component that doesn't have a model.
Okay.
So you can't simulate this, right? So what you do is you see the little, on the active bar at the top, you see that little eye in a circle pin? Right click on that.
That's a
parameter set. Hit escape.
Parameter. Yeah.
Hit escape. Hit escape. Don't place that. Hit escape. Right click on that. Now go down to compile mask. Now you cover that component with the compile mask. Yep. Right. But what that does is it says that whatever's under that thing, leave it out.
Okay.
So don't send it to the board.
Just ignore it.
Don't add it to the net list. Ignore it. It's like it's a comment. It's a graphical comment. So anything you don't want to include in simulation, you can tell it to leave it out.
Okay, cool. I didn't know that.
And so here's the little triangle in the corner, you can have that. You can click on that and it'll minimize to include it when you sync to the board.
Okay. The little triangle in the corner. I don't know that.
The compile mask you just placed over J1. There's a little triangle in the corner.
Oh, I see it. Yes. Oh, very cool. So here's why I had to reach for LT Spice and not Altium, though, is like here's a 2N3904.
There's no
And
model.
there's no model with it off the bat. Whereas with LT Spice, not only is there a standard NPN, but there's also a 2N3904, a 2N222.
That's what I was going to say. Like the reason people don't simulate in Altium Designer is because you use all these parts from the libraries that come with it, and almost all of them don't have a model attached, and that's a pain in the butt.
Right.
This one I see is just sourced from your own schematic lib, mcgsmt.sch.
Yeah, I grabbed it actually just last week off of out of the Altium manufacturer part search, so it's a fresh part.
So here's the thing: you can still go to their documentation website or resources on the website, and they have a legacy downloads section. On that legacy downloads section, you can download all the old PCB libraries that used to come with Altium before they had any of this cloud stuff or any vaults or any managed data. Like Altium Designer Summer 09 was the last version that shipped with about 200 or 300 megabytes worth of libraries you could install as standalone desktop libraries. None of them have 3D models in the footprints. So people generally don't want to use them because you'd rather have the 3D model attached, right? But one thing that you do get in those libraries is all the SPICE models. Not every part has SPICE models, but a lot of them do. Probably, I don't know, about 30,000 of the parts actually have models linked.
All right.
But the problem here, and the other reason people don't want to use Altium or Eagle with the built-in NG Spice engine, right, for simulation is it doesn't support encrypted models.
Tell us about encrypted models and black boxes.
Encrypted models is why TI has a free version of PSpice for download that you can request.
All right. And it's what? It's what it sounds like. It acts like a black box with just pins without giving away how they did it, right?
Exactly. It'll behave accurately according to the
behavioral
silicon.
model. Yeah.
It's according to the silicon. But if you had the original SPICE model source that's accurate to the silicon, they're so accurate now from companies like TI that you might download from that for some of their components, not all, they wanted to encrypt them because it would allow their competitors to reverse engineer some of the silicon. If they could see the SPICE model inside, the SPICE model is also a sub-circuit, and you can make a schematic out of that sub-circuit. And then you can see, oh, that's how they do that. That's how they do this. You know, and especially some of their more recent smart battery management chips or switching regulator controllers and many other things like that. A lot of their valuable IPs wrapped up in that stuff. So it's like, if you could see what was in it through looking at the SPICE net list, you'd be able to copy them. And they partnered up with Cadence and said, you give us a public key and we'll encrypt everything, or however it works. And so the only way to be able to open those models and run simulations with them is if you build an encrypted simulator engine and partner with them for them to give you the key to be able to, I guess the EDA company would get the public key from TI, right? So Altium would have to go to TI, and TI would have to want to work with them in this regard. And
so how would I add a 2N3904? I'm actually trying to find one. That's why I've been doing it in the background. When I download this from Altium, it says models, but they only mean footprints and 3D models. They don't mean SPICE.
That also means simulation models. But scroll down on the properties panel.
Yeah, I'm there.
Scroll down, add, click that add button. Do you have it?
Oh, there it was. It was off the bottom. Son of a gun. Thank you.
You can also add IBIS, signal integrity. I guess that's an area that they keep talking about improving signal integrity, because that's the one weakness Altium has compared with, say, Cadence Allegro or Mentor Expedition,
Right.
or even Mentor pads. You can get license options and get hyperlinks, which is an insanely, it's like the industry, how do you say it? It's like the industry standard, or it's the flagship sort of SI tool that everyone refers back to for quality comparison, right? So Altium has a built-in SI, but it's way, way out of date, and they can't update it because that company that wrote the code they bought was acquired by Zuken in the early 2000s.
I have a question.
Anyway.
So if you
Yeah,
do you often run into a case where you do some stuff in Spice, and then perhaps you go and build the real thing and see that it's drastically different than what your Spice simulation
Oh,
was
there's
showing,
a
or
whole
is
art to knowing if you're troubleshooting the simulator versus troubleshooting real life or not.
Absolutely. And it happens to me frequently, and it's really frustrating. And,
so
like I mentioned, like the most common scenario there is when I'm trying to make an oscillator. But if it's so you have a book? You have a book?
So I was getting into watching this guy, Bob Pease, and if you watch anything about him, he's very negative on Spice. He just watches videos, and parts of his book talk about how people have been fooled by it, but perhaps he thinks he knows better, or maybe he does, Well, and
Bob
he would build
Pease was the guru.
and here he is building something in the air there, right? That's his Spice, whatever.
Yeah, it just takes longer. That's the you have to also decide: is it going to take me longer to build this and simulate it, or less time to just breadboard it?
Shoot a board. Well, or these days, just shoot a board. You get the boards back so dang quick. By the way, Mike, I already got my boards for this. I don't have them for the LMH 1981, but I got them for that circuit we've been playing with.
And I guess maybe you start to learn where you're getting into dangerous areas where you're like, this is probably not simulating correctly. You just get a spidey sense maybe, and you're like,
There is one area where I will always want to start with simulation though, and that's anytime I'm going to deal with high voltages.
Okay. All right.
I'd much rather simulate an electric shock than actually test an electric shock. So high voltage is the one area. And usually that's also where it's really tricky, because I'm probably going to be designing a step up, like a boost converter or an isolated switching power supply that's stepping up voltage, right? And that's one area, that's where some of the more expensive commercial Spice tools, where they have some secret sauce that's worth the money that goes into it. Like here's one. It's called Simplus, and Simplus is not a cheap tool, but they had Spice 3 plus their own engine, which is piecewise linear. And a piecewise linear engine means you're simulating it's event based,
and it has points where it synchronizes or something.
And it means you can have very high voltage and current swings in a circuit, and it will still converge, because the method of simulation is entirely different. Whereas with Spice, it puts all this stuff into a matrix, and it has to go to a point in time and then converge on what all the values need to be based on this complex matrix. And you run into convergence problems with Spice if you start having high voltage and current swings, when it was really originally designed to simulate discrete transistor and early integrated circuits. Spice was first developed in I want to say in the late 60s or early 70s. So it's so some of those tools, that's where the money is in being able to do those different things. I believe TI and others have made it easier by creating better models, but again, some of them will be encrypted, and you'll need to use a tool that allows for those encrypted models. So, but I keep going on and on. I'm sorry. We're 10 minutes from the hour, and I still haven't seen how Mike generated that stimulus, which is really cool.
Yeah, I was going to show the stimulus here real quick that he did, but Mike, can you talk about? So when we're talking about piecewise linear, we're talking about a file that looks like this that basically draws the values for you.
So as you might expect, it's fairly trivial once you have a scope trace to like convert it to that format.
It's just time versus value, right?
Yeah. Especially like my scope, Bill can't get his to do it, but mine will give me a CSV, and it's like and to write a script to do that is pretty much trivial. But it's and then you kind of have to get the time base right. You have to like figure out like how much space is between each sample. But that's And then I made little scripts where you could, if you make like a little part that's repeated, you could make it cycle over and over again if you wanted to.
Right. So we did that for horizontal lines of NTSC. We captured a horizontal line at high definition, and then Mike made it repeat several times so that we could simulate part of a frame and whatnot. Did we do a whole vertical frame? We did, didn't we?
Well, and that's where you start to get into this place where if you go down this road, you can quickly capture too much. And that matrix thing you were mentioning, Ben, will happen. You start the simulation going, and it'll say something about doing something with a matrix, and it'll take 5 minutes before it starts simulating. And that's probably because, like, you could say, well, maybe I'm sampling too much data, and you start thinking about Nyquist and stuff like that, and just getting just enough.
Right, and that's another differentiator. Like some of the different Spice tools, if you just download it, and draw a circuit and try to simulate, and it won't converge. It's sometimes the default settings for the simulator program need to be adjusted based on what you're trying to do. So like you might have there's this set of parameters that drive Spice, like and they're all things like when there's a value within the matrix that's changing, that each iteration on convergence is changing less than some percentage. Then we consider that value to have converged. And then when all of them have, minimal changes from one time step to the next, then we know it's converged. And so that's the value for that time step. And then we move on to the next time step. And sometimes they don't converge. Sometimes based on our circuit, the values might go like wildly up and down, and it can't converge. And some of this can be controlled with the default parameters you put into the system. And some of it's just knowing that Spice simulators work this way, and you have to do things to get them to understand what you're trying to do. So a classic example is you try and simulate a circuit that has two capacitors in series.
It just doesn't know what the charge in each one is, or
it's like
it's like a singular matrix.
So good Spice simulators that come with a library will have a capacitor model that has a default shunt resistance.
I was going to ask you, do you ever seed your drawings with little resistors, like a 1 meg resistor, just to give it a value so that the simulation knows how to start up?
Sometimes, yes. And that's also where you want things like the compile mask in Altium, because I can say during simulation, this component's used for simulation, like it might be a source or it might be a shunt resistor, or but you can also use the global settings of any Spice tool and say there's a global shunt resistance. So every object on every node has a shunt resistance across it, and it could be 100 gig ohms.
Right. But it's something.
But it's enough for it to think the algorithm can cope with.
Right.
Capacitances in series and weird stuff like that. Because there's real world designs where we do capacitors in series, right? And you think of them as ideal capacitors, but they're not. They have a finite insulation resistance.
Yes. They have leakage. They have equivalent series resistance.
Oh my gosh, and that's another topic. It's a good idea to download capacitor models from the capacitor manufacturers, because you'll be surprised how bad
Whoops, we lost you.
Yeah. But if you have a capacitor that's biased, it will have a different capacitance.
Yeah, you're back, Ben. Yeah.
Yes. If you graph the model, if you graph the impedance of a capacitor model that you could download even for a X7R decoupling cap from AVX. They have these really cool online tools that show you the graph of the impedance. You'll see that the capacitor ceases being a capacitor. If it's just a run-of-the-mill decoupling cap, it's only a cap up to about 100 megahertz, after which it's actually an inductor.
Just getting all the real physics involved. Huh?
Yeah. Real electronics. So based on what you just said, I just went to Nichicon, and there is their spice models for different varieties, low ESR. And to your point, Ben, for example, for a switching regulator, it'd be real important to use the real spice model for a real capacitor for a switching regulator.
I should try and simulate one of them right now, but do you have something do you have some of these in LT you could run through?
No, the only thing I have in LT is, and actually I've got it as Mike said. Oh, did it load the whole frame here? No, Mike made a stimulus file for an entire vertical frame. Of NTSC, which we couldn't do in the old days. What's funny is to hear Albert Charpentier talk about that. He said we couldn't simulate an entire vertical frame.
And he had no GUI back then either, right? He'd do it with text files and
it was all text files,
or punch cards. I don't even know if he had a text editor. He probably,
So where's this? You said Aldium. Let me back up once. So Mike, did you happen to open Proteus at all this week to look at the spice in it?
Because no, but that's where I started with
it. Has the models. If you have a symbol that came with Proteus, I think it's got a spice model, but don't quote me on that.
It has a spice. It has a spice variant underneath it that it uses to simulate things.
Yeah,
and it makes me think this is kind of cool because, like, you could almost imagine like a little like competition or something in the Coriolis channels where people are like suggesting various solutions to a problem, and you can share your models and say like, here's my solution, and we can like all like try each other.
We did that this week.
We want to do that. We totally want to do that.
Mike and I did it. We just did it in a private channel, and we should have done it in the chat channel. Actually, we moved it to the chat channel, and we showed them, like, we even did a transistor version of it. We released that to the chat channel at CoriolisEffect.com.
Yeah, so this was the one I was thinking of. I just wanted to share this real quick because it's actually just so excellent, and there's no sponsorship or nothing here. It's just something I came across and found very valuable. Kyocera AVX. Sharing. Oh, Bill's just quickly taking a work call. Kyocera AVX has this amazing set of design tools on their website. So the one you can download the ceramic capacitor models. There's, of course, they make chip antennas for mounting on your boards if you don't want to do your own integrated antennas. But they've got models for all of this for simulation, and they'll simulate the S parameter files, which you can use in coax, which is a free RF and spice tool.
Right.
They've got libraries for ANSYS if you've got the budget for a $200,000 EMAG suite that's incredible and very powerful. But this is the one I got, SpyCat and Spy MLCC. So these are very cool tools because let's go for a regular X7R, let's say general purpose X7R. So we all say, I'll use X7R caps for decoupling your digital boards, and I'm going to go with 0603. So these are our popcorn components, right? And 100 classic, 100 nanofarad. So let's look at this. A typical cap that you'd buy from DigiKey for your project. And look at this. So they give you online, they're simulating.
Okay.
Why am I not seeing a graph here?
And I noticed in Spice you can set the temperature.
Yeah.
You can set like the temperature that your board is running at and or sweep it across. Yeah.
Because these things vary widely. I don't know why I'm not
That's
seeing
fascinating. Yeah.
Let's say I'll see.
Try hitting ESR, see what it says.
Right, so this is equivalent series resistance by frequency. So that's interesting because it's interesting that the series resistance is higher at lower frequencies. So you get this ideal spot down above 10 megahertz. And yet we're talking about these being bulk storage across your board for a chip that's pulling switching transients that have harmonics well up over a gigahertz often, right? So here's the equivalent circuit diagram.
Oh, wow. That's pretty
Like
complicated.
That looks
There
like
you
screenshots
go.
from
There you go.
screenshots from Eagle, I'm sure. But look at this. So they have this is the actual. If you download the SPICE model from Kyocera, this is what's in it.
Oh, wow.
And they're telling you this is how we made the model. We measured the cap in our labs. We measured a whole bunch of them. We got the standard, most common response of everything. And then we built that into a curve fitted model using this circuit structure. And I just find this kind of transparency from the company makes me want to buy their caps. These people are amazing.
Yeah, I love Kyocera AVX anyways, yeah.
DC bias is capacitance versus DC. Now that makes perfect sense. Think about this. What does a capacitor do? Now I'm waxing lyrical about caps, so forgive me.
You can talk forever about caps though, man. They're cool.
What does a capacitor do?
It capacitates,
Stores charge.
Stores energy.
Right? Stores charge. So doesn't it stand to reason that with a physical fixed structure of substrate, the more charge you store into it, the more full it becomes, and therefore the less capacitance it has left to start to charge more. Yes, that's exactly what this means. And of course, and it should not surprise anyone. If you bias a capacitor that's a 50-volt cap and you put 50 volts DC on it, or let's put it this way. I have a 12-volt power supply and I'm decoupling it. So I buy 16-volt capacitors because that's 12 is well within the range. No problem. And yes, they'll store energy at 12 volts, but their capacitance is now less because you've charged them up already to 12 volts.
I forget, does this do these LCR meters do a bias? I don't remember if these do that.
I have the other one. Good question. We should test that.
So I have some other LCR meters, like the old HP ones, that you can put a bias on it, and you can actually see this effect that you're talking about. You can see the impedance change. Right. I don't know if this one.
What's your good LCR meter? Is that an HP or what's not that yellow one? But
this yellow one actually is good. I've compared it to the good one. Yeah.
Right.
The other one's it's an old HP. Yeah.
Yeah. Okay.
That one's a 4262A, but yeah.
And when you're ready to share it, like, I don't know why, but clicking it off the tab and back to the impedance tab shows the impedance again. It's working this time.
Yeah, I wondered if it would be HTML5 thing.
People, this is based on measuring the actual parts off the production line and creating a stochastically accurate model. The minimum impedance of your typical 0603 100 nanofarad decoupling cap with X7R temperature coefficient material is what's this frequency? It's 16. They're really, really good to 17 megahertz.
Right.
So I guess for retro computing, they're perfect.
Well, that's at room temperature. You put it in a freezer, and I'll bet it changes.
Yeah, well, look at temperature. If we cool the thing way down, it loses only about 8%, which is not bad. But
that's not bad.
Your ideal temperature is tropical room temperature.
Right.
35 degrees C.
Right.
And then that's the other thing, they heat up, the whole thing heats up, they drop way back down again. You lose 12% at 105. So these are actually also not bad. Within 10% over that temperature range is pretty darn good, I think.
Right. Yeah, this is a great resource. We should come back and talk about caps on a show. So
and that's just
it's 5 after, and I actually have to jump today, but you guys can keep talking if you want.
Yeah, we could just call it a day. Yeah.
Well, yeah, we can call it. So I just want to finish off with this last thing. And this is something else.
Show us this.
This is not a SPICE simulator. This is another online piecewise linear simulator, and it's kind of geared towards learning.
That looks cool.
It's almost a toy, but it's actually really fantastic for visualizing things in any kind of circuit. So it'll do mixed digital analog, but it doesn't do real time. But it's animated, and this is some people have probably seen this. You can go there and use it for free.
It's everycircuit.com.
Yeah, or just, and again, there's no sponsorship here. It's just something I bought my perpetual license to access this for $14 when it was a new thing. They were launching, and they were trying to see if Altium wanted to partner or something. But the cool thing was I could make a circuit describing how a protection circuit on the Arduino, for example, worked with the MOSFET, and it was animated, and I could embed that in an iframe in a blog so people could interact with it and see it operating, you know. So I just thought that was really cool.
Yeah.
It's not very accurate. You wouldn't use it for serious electronics design, but for describing how something works and just giving it a sanity check.
Yeah, that looks pretty sophisticated. Yeah.
It's a very, very neat little way to do it. So,
well, it looks like a great learning tool for something like the 555, which you've shown here. That's excellent.
Right. Anyway,
so
like I said, when Bill and I were discussing this earlier in the week, and we got onto Spice, I'm like, flip, we could do weeks of content on Spice, but I thought I might save that for an actual course or something down the road. But yeah, we can always come back to it.
Yeah, the live format doesn't lend itself to actual instruction very well. We're pulling in so many directions as we talk here, unfortunately.
That's the fun of it, though, too. Like, oh, look at this! They've got relay models in there.
That's cool looking. Yeah,
this is like the old. How do you use relays to make a old school vibrator?
Looks like a 4-cycle automotive engine or something. That's pretty cool looking.
It's a relay based DC to AC converter from yesteryear.
Okay.
Yeah. Here's a small can.
Yeah, that's one of them. They buzz away.
Yes, they do. And they'll knock you on your ass because a lot of times there's an inductor involved.
Well, and you relay coils.
Yeah.
Yeah, those relay coils will give a jolt.
Right.
Fun stuff.
Excellent. Well, hey, I want to thank everybody for showing up for this, and check us out at Coriolis-effect.com. Get the Discord invite from there. We did do a kind of a challenge this week of like how I can fix that in 3 transistors type thing. And we came up with lots of different answers for how to do it. So it was a lot of fun.
Totally.
Thanks for having me on. I'm hooked on this stuff. This is pretty cool. Yeah.
Oh, yeah. Oh, leave it to Mike to change the bar then. I show him Spice, and next thing you know, he's writing these huge stimulus files for me. You know, but think about it. If you could see it with your scope, you could simulate it now because we suck it into the scope, turn it into a piecewise linear file, and blow it into Spice or into the arbitrary waveform generator, and now you've got your own, you know, a repeatable version of whatever it is you generated.
Totally.
Very cool.
So cool. Always a pleasure having you on, Mike. Thanks for joining us.
Yeah.
Yep.
And good
seeing everybody. We'll see everybody next week. We've got Kerry Sagety, an old friend of mine from Commodore on, who is a broadcast engineer, knows NTSC, and we want to talk about old broadcast engineering kind of thing. So it should be a lot of fun. Plus, he's a character. You think I'm a character. He's a character. So, all right. Well, thank you, everybody. We'll catch you all next week.
Yes.
All right.
See ya.